Let me see if there's anyone who still needs permission. Please let me know. I'm doing it as we go along, though.
Can I also get permission to record? This is Andy.
Okay. Yes, you got it. At least I hope you got it. Let me know.
Thank you.
Sure. There are a couple people I can't do because they're probably on iPads, but besides that, I think I got most of the people. If not, let me know. Okay, let me switch over in the meantime to OneNote. And make sure you can see it. Okay, but this is not your class. This is a different class. But I think at least you can see the screen. Okay, this is more or less where we ended last time. So we switched over to section 2.4, and we have a definition of what it means to be an inverse. And our definition is this. It's called an inverse. A t going from b to w is linear. Of a function u going the other way around from w back to b is called the inverse. Is if you compose t with u and u with t, you get the identity on whatever vector space you're going from. So that's our definition of what it means for a transformation to be invertible. We talked a little bit about the notation of it. So we use this thing that looks like an exponent, but it really isn't. We raise t to the, looks like we're raising t to the negative first power, but we're really not doing that. That's a superscript, not an exponent. So it certainly doesn't mean this. It doesn't mean what it used to mean in numbers, where if you raise 3 to the negative first, you just got a third. Here, the notation is this. So if you multiply a transformation times its inverse, that's how we refer to this, you'll get the identity. But again, this is mostly just notation, which means it's not a meaningful exponent. And there were some facts on page 100, which I think I worked through one of them. This was one of them. If you took the inverse of the product, then it turns out to be the reverse product of the inverses. Reverse meaning the order was reversed. And we went through it and verified that it had all the conditions we needed. So this is the claim, and we actually checked that if you multiplied the composition this way with its inverse, you'll get this. And the same thing is true if things are turned around. If you, well, I think this is, yeah, we have to show it works on the other side too, right? Because our definition here. Yeah, so if you want U to be the inverse of T, you have to show that composition T with U is IV and composition U with T is IW. And that's what we did here. I left a couple of these other facts for you to do, maybe, yeah. And gave you some homework, mostly reading in section 2.4. And then maybe did a problem or two. What I would like to mention, let me see. Oh yeah, these are some true false questions I did afterwards. What I would like to mention is there's something important that I did not mention in section 2.3 that I would like to go back and pick up before we go on with inverses. So let's do that. Let me see if anyone else has come in the meantime here. So I'll stop sharing the screen for a second, see if anyone else has arrived. Juan, I don't remember giving you permission, so I'll do that right now. John, I don't remember giving you permission, so I'll do that right now.
Officer.
Did I miss anyone else? Yeah, you got it, I hope. Brett, I don't remember giving you permission, so I'll just give it to you right now. And I'm looking for any other names that I don't remember. Okay, if I haven't given you permission, please speak up. Great. Okay, so I think we're good that way. Let's go back to where we're doing. And so let's start today. Let's get a new slide. So let's advance this slide. Well, add a slide to it, that will work. Okay, so let me go back and pick up what I wanted to talk about. I sort of didn't get to back in section 2.3, and then we'll go back and talk more about inverses. So that's the immediate agenda here. Nothing new on the midterms, but it's getting closer for me to take care of that. So, and if there's anyone who hasn't taken the midterm or did very badly, I've been asking people to contact me on that. So let's see, 2.3. What I wanted to mention is there were a number of theorems that I skipped over, but one of them I don't want to skip over. And that's theorem 214. So let me put that on the board. So theorem 2.14. It's on page 91. And it reads as follows. Let V and W be finite dimensional vector spaces having ordered basis beta and gamma. And let T be the linear transformation. So it's the usual setup. Let's write it in a little bit of a different order. Let's suppose T is going from V to W, and T is linear. And of course, V and W are vector spaces. And V comes with the basis of alpha, and W comes with a basis, an ordered basis of beta. So that's the structure. Those are the assumptions. So if you want, you can label all this assumptions. Okay. And here's the conclusion. Conclusion. For each U and V, for each U, vector in V, we have the following. If you take the matrix associated with T, so that's what we were playing with in this section, in the previous one. But you don't look at it, you look at it after you let T work on U. Okay. So that's the matrix associated with TU, and TU is, of course, in W. So this would be the matrix associated with gamma. And it tells you, in order to do this, what you need to do is take the matrix associated, take the T matrix. Okay, and that's the one. Oh, first of all, I have the ordered bases wrong, so that's no good. They're listed as beta and gamma, so let me correct that. It should have been. So the ordered basis for V is beta. The ordered basis for W is gamma. Okay. So if you take the matrix associated with T going from basis beta to gamma, which is this, and you multiply it by the basis U, as written in, multiplied by the vector U, rather, as written in basis beta. Okay, so what this is saying, let's see if we can do a nice example of this. Well, they do have an example. Yeah, let's do the example. I think the example will probably be as useful as anything I can do. So this is the conclusion. It's telling you that if you want to see where you are in W, so you look at the transformation of U and you form the basis of, you form the matrix associated with that in the gamma basis. that's the same as taking this matrix and multiplying it by this one. Let's do the example. I think the example will be useful. So example 3. So let's see example 3. Example 3 should be a follow-up to an example that I think we've already done. So it says let T go from the polynomial space P3, from the vector space P3 to P2. So that's what this example is about. T goes from the vector space P3 of R into P2 of R. And how does it work? Well, you give me a third degree polynomial, and it takes the derivative of it. So if you given some polynomial here, this transformation, it just takes the derivative of it. Okay. And according to example 4 in section 2, so we can just repeat this if we need to. If we look at the matrix A, which is corresponding to this transformation, let's make sure I'm going the right way. Yeah, going from beta to gamma. Okay. They say we've done this before and it's equal to this. 0, 0, 0, 1, 0, 0. Uh, 0, 2, 0. And what else? 0, 0, 3. And they refer you back to example 4 of section 2.2. So see example 4 in section 2.2. But I don't think it's that, I don't think we actually need to spend much time doing that, because basically just to quickly recall what we're doing, beta, the standard basis in here would be 1 x squared, and x cubed. So that's what we used as the standard ordered basis of P3. And when you take the derivative of 1, you get the constant 0, which in terms of this, so I guess I should say what gamma is. Gamma is 1x and x squared. So in order to, so if you actually wanted to see what t of 1 is, it's 0, because the derivative of 1 is 0. And if you put that in terms of this basis, it would be 0, 0, 0, which is the first column. Similarly, t of x, we just differentiate this, which would give you the 1. And now if you put that in terms of this basis, you'll just get 1, 0, 0, which is the second column here. So this is the usual thing. You figure out where the base vectors go and turn them into columns to form this matrix. So I'm just reviewing that quickly. And what happens to x squared? When you differentiate it, you get 2x. So in terms of this basis, it would be 0 times 1, 2 times x, and 0 times this. So it should be 0, 2, 1, 0, 2, 0. And that's the next column. And then finally, where does t of x cubed go? t of x cubed becomes 3x squared. And if you put that into in terms of this basis, it would be 0 times 1, 0 times x, and 3 times x squared. And that gives you the last column here. So that's an example. I'm sure we did, but I just redid that part of it. Any questions thus far? Okay, so that's what that looks like. And where they're going with this is they're trying to illustrate this. So let's see what they do next. Flip the page, I guess. We illustrate 214, which is what the theorem I just gave is, by verifying all of this to be true. So what they're saying is theorem 214, which is stated above, in this context looks like what? So they rewrite this theorem right here. And they say what that theorem says in this context looks like this. Take t of some polynomial and form the matrix corresponding to that in the gamma basis. And that's equal to this thing, beta to gamma, times what you get when you take the polynomial p of x and you formulate it in basis beta. So this is just a rewrite of this, where u is replaced by p of x, basically. So if you replace u by p of x, which is what the vector is here, some vector in V corresponds to some vector in here, which they're calling p of x. So this is what theorem 214 looks like in this context. Okay, and we've already figured out this part of it using this transformation. So we already know this part of it. So I'll put a check underneath that because we know that. Then we illustrate this by verifying this. Okay, so they're going to check it for a particular case. So they're checking it. So they're checking this theorem 2.14 when the polynomial that you start with is, and they write it in this form, 2 minus 4x plus x squared plus 3x squared, 3x cubed rather. Okay, so if you choose the polynomial to be that, which is a third degree polynomial, then they're saying let's just track what they're saying here. Let q of x be what happens when t works on p of x. Okay, so what happens when t works on p of x? Well, what does t do? T differentiates this. So what you would get would be the derivative of 2, which is 0. The derivative of this would be minus 4. The derivative of this would be 2x. And the derivative of this would just be 9x squared. So this is what t of p of x is. And why do we need that? Well, we need that because what we want is what's over here. And what's over here is essentially saying take this vector, which is in P2. Okay. And just look at it in the gamma basis. So the gamma basis is the standard basis 1x and x squared. And it's already in that form basically. But in order to get the appropriate thing over here, we have to turn it into a column. And that's what they do. So in this case, if you want to make the matrix associated with this, it's going to be this matrix turned into a column. -4, 2, and 9. With sort of clear changes, if the polynomial is something different, whatever it is, you would be figuring out t of p of x in a similar way and changing it into a column. Okay, so we have now this. Okay, we have two pieces of the puzzle here. And they say, but the third piece of the puzzle is this part over here. So what is that? Well, there you take the polynomial p, which was this guy, and because we're assuming that, and we're turning it into a matrix corresponding to the basis beta, which is this. And how would you do that? Well, it's already in that form. It's already a linear combination of the base vectors in beta. The only thing you would need to do over here is make a column of it. So whenever you take transformation or a vector in a particular basis, you just turn it into columns. So p of x beta, in this case, would be the column that has this as its entries. So 2, -4, 1, and 3. Okay. All right, so now we have everything that this is talking about, but it's got so many letters that it's sort of easy to get confused. But now let's see what the statement is saying. What the theorem is saying is that if you take this guy, and I guess that's this, but I didn't put the gamma down here. If you take that guy, which is 4 minus 4, 2, and 9. So 4 minus 4, 2, and 9. That's what you'll get if you do what? If you take the matrix corresponding to this, which was this guy. So it's 3 by 4. And I don't remember all the rows. So the first row is 0, 1, 0, 0. 0, 1, 0, 0. Second row, let's scroll up, is 0, 0, 2, 0. 0, 0, 2, 0. And third one is 0, 0, 0, 3. So that's that matrix there, and then multiply it by the matrix that you get here, but we've already done that. That's equal to this thing, which is 4 by 1. And here it is, 2 minus 4, 1, and 3. Okay, so this is the content of what theorem 2.14 is saying. And of course, you could check it. If you multiply this by this, the only survivor will be the 1 times -4, which is this. And if you multiply this times this, you'll get 2 times 1, which is this entry. And if you multiply the last row by this, you'll get just 3 times 3, which is 9. So the whole thing works. Okay, so this would be an explanation by example, at least, of what this theorem is saying. And now that we have it in front of us, well, let me see. I don't think there's anything more to say. No, that ends the example. So any questions on the example, at least? Now, what it means to me, let me see if I can put this into colloquial or an everyday language. What it means to me is if you have a transformation, a linear transformation from going from B to W, and you turn it into the matrix, what you need to, what this theorem is saying is if you have a vector in U and V, which is U, turn that vector into its basis in beta and make a column vector out of it. And if you multiply the transformation matrix times this column vector, what you're going to get is what comes out of the transformation. So if you find the matrix of the transformation, and that's what's in the new basis gamma, that's what's coming out of this. So essentially what it's changing is it's changing the transformation into matrix multiplication. Find the matrix corresponding to the transformation, multiply it by a vector in the basis of your domain, which is V, and what comes out is the vector that comes out of the transformation. So you can think of what it's saying is really important. It's saying that you can think of any linear transformation as matrix multiplication of that. Find the matrix corresponding to that transformation, represent a vector U in the base in V as a column, multiply this matrix times this column, and what comes out is what T does to U in the new basis. So this is saying basically transformations work like multiplying a matrix times a vector, giving you a vector. That's the content of this. Now, so that turns out to be important because it's telling us now that anytime we have a transformation, we can really just think of it as a matrix times a vector, matrix times a column vector, I guess. And the column vector is what the transformation does to U. So everything now is in terms of either a matrix or these are matrices too, but they're matrices that are special. They're what? They're just column vectors each. So they're, m by 1 kind of vector matrices, but that's what this is saying. Now, I don't know if I want to take the time to do the proof now. Maybe I'll assign that for homework because I do want to get back to inverses. So now that I've done the example and I've explained what this thing is doing, try to do the proof yourself. Read the proof. And see if you have any questions. It's all there in the text, but it does refer to some past theorems, hopefully past theorems that we've done. But anyway, so I'm trying to include this among what we're doing in this section. Read the proof for understanding. And if you have questions, we can go over it either after class or some other time. Before I turn away from this, any questions about this example? I think the example is very illustrative. It does give you a feel for what's going on. It would even be probably, in my mind, a better example if they didn't mess it up with polynomial vectors. That's okay. I mean, what would be an easier example of this? If they just told you you're going from R4 to R3, which is really what they're doing here. And then it would be all in terms of, vectors that you're a little more familiar with, but that's okay. All right, questions? Let's flip the page. Wow, I messed up. Try it again. So let's go back to where we were when we stopped yesterday, or the other day rather, is on inverses. So there were these facts to establish, and there is a major theorem here that we need to cover as well. So we're back on now page 100. So back on page 100, take a look at the next theorem that we're considering. It's theorem 2.17. I'm getting used to doing this kind of phrasing. Let's think about what the assumptions are. So the assumptions in this case is that we have T going from V to W as usual. And as usual, V and W are vector spaces. And T is assumed to be linear. Now, what we just came from the previous section, T is linear, which means if you like, you can think of T as a matrix, because that's the whole point of that section in most of this chapter, is that linear transformations can be represented by their matrices. Okay, so you're assuming all of this, but you're assuming something more. It's linear and invertible. So we also assume T is invertible, which means what? For us at this point, that means there exists a T inverse such that what? Such if you take T inverse, and you take T inverse T, you're going to come up with the relevant identity element of the identity operator for transformation. Which one is with this? This is going from T goes from V to W, and then this goes from W back to V. So this would be this guy. And this one goes from W. So that would be this too. So for at this stage, T is invertible means this. Conclusion, or then, what's the conclusion? If you look at T inverse, T inverse, which goes from W back to V, well, we want to say that that's linear. Is a linear transformation. Okay, so that's the content of the theorem. You might say, well, that seems sort of reasonable. If T itself is linear, why wouldn't its inverse be linear? But if you think a little further, you'll realize that you're making an assumption by that. Something could have an inverse without it being a linear transformation. So, for instance, for instance, in calculus, if you were given the function, say x squared, what would the inverse function there be? Let's assume x is positive here for now.
The square root of x.
Square root of x, right? Okay. So, but this function looks like, looks like a parabola on the right side, because we're assumed x is positive. And this one over here is sort of a parabola on its side. That's how the square root function looks. So this one looks like this, and this one looks like this. but neither one are linear. There's one is the inverse of the other. So if you take the square root of x squared, you'll get x. And if you square the square root of x, assuming x is positive, you'll get x. You'll get x as well. Okay, so both ways you end up with the identity. So this is just like a math 3100 example of a function and its inverse, but neither one are linear. Okay, so all we're saying here, if you were to put it in context of lines, it would be saying, let's think about it a little further in terms of lines, because that puts it back into something that we're familiar with from calc. So if you had a function that looks like this, f of x, say it looks like x plus 1. And that's what y is. If you wanted to find its inverse, assuming it exists, you would typically solve for x. So that would tell you that x would be what? Y minus 1. And this would be sort of the inverse function going as a function of y, I guess. And you can see in this case, this is a line. Well, this is also a line. You could graph it again in a different system, but they're both lines. And that's pretty much what this thing is saying, is you start with something that's linear and it has an inverse function, then the inverse function is going to be linear as well. Well, okay, this makes it very reasonable in terms of calculus, because you can see that if you compose these two, if you were to take f of x and take f inverse of it, if I do it right, let's see, I'm doing x plus 1. That's what f of x does to it. And then I'm taking the inverse of it. Well, what does the inverse function do? It takes this and subtracts 1 from it. And yeah, lo and behold, you do get the identity. Okay, so here, this is not a hard thing to verify. And you can verify that it works the other way around. If you were to take f inverse of y and then take f of this, f inverse of y is just y minus 1. And then if f works on that, what does f do to anything you give it? It takes it and adds 1 to it. The ones cancel and you get y. So this is an illustration of how we would verify this result if we were just in calculus and if the functions are linear. And we're just noticing that if you solve for x as a function of y, it turns out to be linear here. Well, we're saying that holds in general, with our general definition of linear being between two vector spaces. And it doesn't have to be, just R2. It could be, could be vector spaces like we just talked about, polynomial vector spaces, or it could be matrices or a variety of things. Okay, so that's what this theorem is about. It's saying that if you have a linear function and it has an inverse, then that inverse itself is linear. That's the content. Let's look at the proof now. So the proof and by the way, put another way, we're saying that linear functions, if they're invertible, their inverses will be linear, which means it retains the property of linearity. That's what this is all about. Okay, but how do you prove it here? So here's the proof, somewhat short, and it's straight out of the book. So let's go through it. Let y1 and y2 be in W. Let y1 and y2 be vectors in W. W is the codomain of T. So let them be any vectors. And let C be something in the field. Okay. Since T is onto and one-to-one, note that T is onto and 1-to-1. Why is that? Because that's equivalent to being invertible. Back from Math 3100, a function going from one space to another, an inverse exists only if it's 1-to-1 and onto. So this is equivalent to T being invertible. And this is a case where we're referring to the result from Math 3100. Okay, so knowing that T is invertible means that it's 1-to-1 and onto. Then there exist unique vectors x1 and x2 such that this happens. So there exist unique I could spell unique. It came out the way I like. It didn't. And the unique vectors are in V such that T of x1 is U1. T of x1 is Y1 rather, and T of x2 is Y2. Okay, so the picture is this, if it's helpful. This is V, this is W. Y1 is over here, Y2 is over here. Because it's 1-to-1 and onto, onto means that these places came from somewhere. Call the places they came from x1 and x2. Coming from them means that if you take T, you'll get this. T of x1 will give you y1, which is what this is saying. And T of x2 will give you y2, which is what this is saying. And then they're also saying that these two vectors are unique. That means what? There can't be another vector over here that goes to y1, y. If there were, then it wouldn't be 1-to-1. Two vectors going to the same thing is contradictory to T being 1-to-1. And we know T is 1-to-1 because it's invertible. So we're saying that for any y1 and y2 and w, there exist unique vectors x1 and x2 that have this correspondence. And unique means there's not another one back here that goes to there, and there's not another vector over here that goes to this. Okay. So that's the setup. Now, with that being said, since the inverse exists, and it goes the other way, what must be the association? T inverse of y1 goes with x1, and T inverse of y2 goes with x2. So the inverse function goes the other way, and if you want to picture that as something going this way, that's fine. Taking you back from y1 to x1. Okay, so there's a little picture that could be helpful. All right, so we've got all of this. So now we're set up to try to show linearity. Now your book says it's enough to show, it's sufficient. To show to show what? That if you take the inverse transformation of a linear combination of the y's, what they want to show is that this is the inverse of CY1 plus T inverse of Y2. Okay. And what, okay, but we've gone through this a number of times already. This is the book's simplified way of showing that a transformation is linear. My way of doing it, which I've sort of been using throughout here, would be to show the T inverse of Y1 plus Y2 is what? T inverse of Y1 plus T inverse of Y2. That would be one condition, and the second condition would be T inverse of some constant. I guess that constant is being called what? A here, I think. C. Okay, so some scalar working on some y value would give you C times T inverse of y. So this is how I've been showing things are linear, and I've been calling things being transformations. I call this the linearity condition for the vector addition, and this is the scalar multiplication identity for this operator or transformation to be linear. But they do it all in one swoop instead of doing each of these individually. They're doing it in one swoop. You could do it the way that I've been doing in the past if you're comfortable with it, but for a change, let me just follow what they're doing. It shouldn't be a big deal either way. Okay, so this is what we need to show. This is from some past result earlier in this chapter. Okay, so we start with this. This is what we want to show. So start with this. Start with the inverse working on C Y1 plus Y2. Okay, that's what they start with. And all they do is they put in what we know. So this is the same as T inverse C, but Y1 by this is T of X1. And Y2 is T of X2. So from here to here is just by substitution of this and this. And let's see, yeah, I think I have the parentheses matching up. Okay, so that's just substitution. What's the next step? The next step is, well, you know that T is linear. So you can write this as T inverse. And you can write what's in the parentheses now as T working on C X1 plus X2. And all we've done here is make use of the fact that T is a linear transformation. So T of this would be equal to that by linearity. So the reason here is linearity because T is linear. Okay. And the next step is just to say the following. T inverse can be thought of as working on T. And the whole thing is now working on CX1 plus X2. So doing one composition after the other is what we're calling product. But we already know that if you do T inverse composed with T, you come up with an identity. It's the identity on, I suppose, let's see, on V, right? They don't even call it that, but that's okay. And so this is from the definition of what an inverse is about. Whenever you compose, this is our definition of what an inverse does. When you take the inverse of a transformation times the original transformation, you get the identities. So this is from our definition of what T inverse is about. Okay, but the identity working on this vector is just this. Okay, and that's just the definition of the identity. The identity transformation just leaves the vector untouched. It gives you back the same vector. However, now we can use these guys. So let's substitute that in here. So this is C and X1 given by this equation right here is T inverse of Y1. So that's T inverse of, what did I just say, Y1 plus X2, and X2 is this guy, T inverse of Y2. And the reason for this are these two equations. This one and that one. So when we see X1 and X2, we can write it as T inverse of Y1, T inverse of Y2. And now we're done, because starting from the left side, we got what we said it sufficed to get. We got the thing on the right side down here. So we're done. Okay, if you look at the proof a little closer, yeah, it's quick enough to just do it again fast. You're trying to show this, which is a combination of these two things. And you're putting in that if you have any Y1, Y2, you already know it came from someplace over here in this diagram. X1 and X2 in this way. So you already know these equations hold. Y1 is T of X1, Y2 is T of X2. And then just go through the steps. Taking the inverse of this, you can put in that Y1 is T of X1 and that Y2 is T of X2. And when you do that, T is linear by assumption. So that means that what's in the parentheses here is this by linearity. And this just means one transformation is going straight after the other. So that's composition. The product is composition. But by the definition of what the inverse is all about, when you compose T with its inverse, you get the identity transformation. So that leaves this unchanged by the definition of the identity transformation. But then you can go back and use these two equations, which were true again by the definition of inverse. And basically because it's 1-to-1 and onto. So you use those two definitions to replace what X1 and X2 are. And if you look from start to finish, you've got your linearity condition. Okay, so this is a much more general proof than the little thing I sketched with up here with just particular lines. but it's pretty cool how it all works. Questions on the proof? What they do next is go to matrices, which is important. So let's follow suit there. So after having theorem 217, it follows from earlier results. Let's see what they say. Now follows from 2.5 that T is linear transformation between vector spaces of equal dimension. Then the conditions of being invertible one-to-one are all equivalent. Okay, so that's an important remark, actually. I'll just restate it. Remark. Suppose you're going, suppose your transformation T is going from V to B. So that's a special case. That's a special case where the codomain is the same as the domain and V is a vector space as usual. So if you're in that situation, no, it's not quite saying that. Take it back. You're going from V to W. So you don't have the same vector space, but you have two vector spaces, V and W. Here's what they're assuming, where the dimension of V equals the dimension of W. So suppose you, okay, so it's more general than I was first saying. Suppose T is going from V to W, both vector spaces, but they each have the same dimension as each other. If you want to call the dimension N, that would be fine. Where N is like a natural number. Okay. In that context, then the following three conditions are all equivalent. What are the conditions? One, T is invertible. Two, T is one-to-one. T is onto. Okay, so their little remark here is saying that if this is the situation you're in, where the transformation is going from one vector space to the other, but the vector spaces have the same dimension, then if any one of these conditions hold, then all three hold. And you might ask why, and the equivalency between 2 and 3 was already established in the theorem they referred to, I believe. So theorem 2.5. So this follows. So if you want to know why this equivalence holds, you should go back and look at what? theorem 2.5, page 71. And I'm confident that will tell you that 2 and 3 are equivalent to each other under these circumstances. And the new thing that you have is 1. And so what they're saying is that in that case, when there's invertibility, well, again, if it's invertible, you know it's 1-to-1 and onto. That comes with the game. So that means that you can just put this as a third condition, which is equivalent to the other 2. Okay, and that sort of follows. Okay, so the main result is saying that 2 and 3 are equivalent. That follows from this theorem. T being invertible follows almost immediately because something is invertible if it's only 1-to-1 and onto. So if you have this, you certainly have each of these. And if you have either one of these, then you have, and it's invertible, then you have the other ones, and then you have all of them. So that's sort of an argument that's going on here.
And just to make sure, Professor, T is just a function going from the vector space V to W. There's no need for it to be linear or
no, it should be linear. I left that out. Thank you. Where T is linear. No, definitely you need linearity. Let's see. Yes. Thanks for that correction. You need linearity because that's the only way you're going to get the condition we just had, actually. What they do now is they start transferring all of these things to matrices. So instead of talking about transformations being invertible, transformations being invertible means what? T times T inverse would be I, and T inverse times T would be IW. So we defined T inverse to be a transformation that makes these true. The theorem we just proved is that T inverse itself is linear as well. So the inverse of a linear transformation when it exists is linear. And so now it's natural to think about what happens when both of these are matrices. So when both of these are matrices, if the matrix T is going with say A or something like that, well, I guess it doesn't matter. Suppose the matrix going with this guy is A, and the matrix going with this guy is B. So if we're thinking of the linear transformations, each of these to be matrices, then we'd want the product of these matrices to be, in this case, the identity matrix on V. And similarly over here, AB would be the identity matrix on W. Okay. And it's natural, given the remark they just made, is to look at this when these have the same dimension. So if these have the same dimension, suppose the dimension of everything here is n, then it's interesting to think about when does what this thing over here corresponds to is 2 matrices giving you the identity. And let's just call it I sub n, since we're assuming everything is n-dimensional here. Okay, so if you're trying to think about what invertibility meant for the transformation, what does that imply for the matrices corresponding to the transformations? It means that the product of 2 matrices would have to commute first of all. So you'd have to have AB equal to BA because they're both equal to the same identity matrix. And so they give you an example, which is a decent place to stop here, I guess. Look at example 2. So in example 2, they say the reader should verify that the inverse of 5723 5723 is 3 minus 7 . Okay, well, that's easy enough to do. Let's just do it and call it a day. 5723 times 3 minus 7 minus 2, 5. So in the usual sense, you're going to end up with a 2 by 2. 5 times 3 is 15, minus 7 times 2 is 14, so this is 1. And if you did this, 2 times 3 is 6, minus 3 times 2 is 6, so that would be 0. And then doing this times the second column would be 5 times minus 7, which is 35, and then plus 7 times 5, which is 35, so this is 0 again. And then finally, last row times the last column, 2 times minus 7 is minus 14, 3 times 5 is 15, 15 minus 14 is 1. Okay, so that's the verification there, that's half the verification. And you can, I'll leave to you to check the other one, but it's just virtually the same kind of thing. Now, why do you have to check the other one? Because knowing the product in this order doesn't necessarily mean that the product in the opposite order works, right? So, so this is the opposite order, 5, 7, 2, 3. And why don't we just do it since we're here? So this row times the first column, 3 times 5 is 15, minus 7 times 2 is 14, so that's a 1. Let's do the first row times the second column this time. 3 times 7 is 21, minus 21, so this is 0. Minus 2 times 5 is minus 10, plus 5 times 2, that's 0. And then finally, this times the last column, minus 2 times 7 is minus 14, plus 15, so that's 1. Okay. So this is mirroring these. So invertibility conditions are the product of a transformation, then its inverse transformation should be an identity. And if they both have the same dimension n, that would turn out to saying that when you turn these to matrices, the product of the matrices should both be giving you the identity. Here's a question. How many of, so what does that mean? What this means in terms of matrices is if we're calling, let's call this one A, call this A and call this B. What we would then want to say is that this B is really what? The inverse of A, if you like. And over here, when you're doing B times A, that would be corresponding times this kind of product. So if you're looking for the inverse of a matrix, you're looking for another matrix that has the same dimension, and that if you multiply by that other matrix in either order, you get the same identity. So in this context, what can we say? We can say if I lost my screen. if A is equal to 5, 7, 2, 3, then A inverse would be equal to the other one here, 3 minus 7 minus 2 and 5. And here's a question for you. How many of you know if a 2x2 matrix is invertible? How many of you know the rule or a way to get A inverse? So that's a rhetorical question, but it's a good one to end on. So put your hand up or gesture in some way. Do you know how to find the inverse of a 2x2 matrix? Yeah. Well, I've got 3 people with their hands up. What I'm suggesting is you probably had that, because in any course on matrix manipulation, or they would go over such things. So you might want to review 2250 or whatever prereq you had for this course. The 2x2 is the easiest case. Well, okay, a second easiest case. What's the first easiest case? The 1x1. Okay, so if you have a matrix that's 3, then you should know that its inverse matrix is 1/3. And there you just only have to find the inverse of this number here. And it's easy to see that if you multiply these two 1x1 things in either order, you get 1, which is the identity. So that's the easiest case. The 2x2, finding the inverse, is the second easiest case. But if you don't know the formula, then this is sort of being a rabbit being pulled out of the air, or out of a hat, I guess, because they just gave you this guy and they say, look, it works. But the real question is, how did they come up with this? And that's what we're going to talk about a little more in the second chapter than this. Okay, I'm well over time. Let me take a little water break for myself. Oh, do I have any problems to give you? Maybe. Did I give you problems in this section already? Did I give you future homework? I'm not sure I did or not. But number 2 would be one. So homework. Problem 2 in section 2.4. I think we could probably go back. More homework. No, let me call it. I'll give it, but I'm not sure I want to talk about it yet. We'll see. Problem number 12, back in section 2.3. I think that's good. So for those who are hanging with me for the office session, I'll see you shortly. For the rest of you, I'll see you Friday. Thank you.